Finally, we would like to talk about quadratic programming. We start out explaining quadratic programming using real variables. The variables that are being used are denoted by x, and x is a vector in Rn that is a vector of real variables. What we can observe is that, identical to before, we have a set of m linear inequality constraints. So the constraint functions in quadratic programming are still linear. To define these constraint functions, we have this matrix A that is an element of Rm cross n. That means we have m rows, and each of the m rows of the matrix defines the coefficients of one linear inequality. So again, every row of the matrix defines one linear inequality. And we have columns of the matrix, n columns, and each column corresponds to one dimension of the variable vector x. On the right-hand side of these linear inequalities, we have the vector b, and b is an element of Rm, so b has m components, and each of the entries bi, each component of b, is the right-hand side of one inequality. So the ith component of b is the right-hand side of the ith inequality. From linear programming, we are used to this term C transpose x, and that is a linear part that still remains. C is an element of Rn that is a vector of coefficients of known entries, and each component of the vector C corresponds to one component of the vector x and is the linear weight of the component of the vector x. What is new here is this term 1/2 times x transpose qx. Let's try to at least draw a two-dimensional example. So here we have the vector x transpose with components x1 and x2. Then we have the matrix Q, and then again we multiply with the vector x that has two components, x1 and x2. So I drew that in there, and now for the matrix, since these are coefficients that are known, I will make up some arbitrary values. So we'll start with 4, and then maybe there's a 1 here, and then we have a symmetric matrix, so there needs to be another 1 here, and there can be a 3 here. Multiplying this out will yield the following function. So first we can collect the quadratic terms. That is 4 times x1 squared and 3 times x2 squared. To that we add the mixed terms x1 times x2, and so we have 1 times x1 times x2, and here another time, so in total this will be 2 times x1, x2. One thing to note is that if the matrix Q is positive definite, then this optimization, having only real variables, is convex. And one would generally hope, then when dealing with quadratic programming, that one has a convex matrix. In order to switch to mixed integer quadratic programming, we'll just basically have the same equations, just now we have mixed integer and real variables. And the difference is only seen here, where the vector of variables x has two subgroups of variables. The first subgroup will be integer and the second will be real variables. One established term for this is mixed integer quadratic programming, or MIQP for short. One problem that everybody should know is the quadratic assignment problem. As input, we have a set of n facilities that we index with this variable I, and we also have a set of n possible facility locations that we index with this variable j. Like the linear assignment problem, the goal is to assign facilities to locations to minimize the cost. However, the cost is now modeled in a more complicated way. We're not only looking at the cost of assigning one facility to one location, but we are modeling the pairwise interactions of this assignment. So we have a cost that isCijkl for a pair of assignments. So the first pair is indexed with ij and the second with kl. So the cost is for assigning facility I to location j and facility k to location L. So when I first read this, especially because there's some graphics papers that also confuse this slightly, I think it's important to note that there are these two different variations of the problem. And one variation allows this cost to be modeled completely arbitrarily. So for each combination ijkl, an arbitrary cost can be assigned. And a second variation only allows a limited form of this modeling, so every costCijkl has to be modeled as the product of two other functions. SoCijkl is the product of fik and djl, where fik is a flow between facility I and k, and djl is a distance between the facilities j and l. And this is the classical quadratic assignment problem. As variables, we still have xij equals 1 if facility I is assigned to location j. And again, note we have n squared number of variables. The objective, however, has n to the power of 4 terms. We have to sum over all combinations of I, j, k, and l. Each of these indices has n possible choices, and we sum up this thing where each term of the sum has a costCijkl, and then we have the product of two integer variables xij and k and xkl. So this models the interaction between the assignment ij and the assignment kl. Again, xij is 1 if facility I is assigned to location j, and xkl is 1 if facility K is assigned to location L. So the cost is incurred if both of these assignments are true. So that explains why we have a lot more terms in the objective than we have variables. As constraints, we have the binary constraint that all variables need to be either 0 or 1. Then, identical to this other assignment problem, the linear one that we discussed, we have non-overlap. Each facility I has exactly one position, and this is modeled for all I, sum xij equals 1. There will be n such equations. Then we have coverage. Each position is covered by exactly one facility. So for all locations j, we have this equation sum xij equals 1. Again, there will be n such equations. I do like this one particular survey, which is quite easy to read, and so I recommend. We're going to give some examples for papers that use formulations that are related to quadratic programming and quadratic assignment. So one example is quadratic assignment for images. One starts with a set of images. So we have n images, and there are n possible positions where an image can be placed. The images itself have some distance between them, so there are distances dij between images. This could be, for example, distances computed on features extracted by a neural network. And then the possible image positions also have distances. These typically might be Euclidean distances in the space where the image positions are located. And the costs are modeled asCijkl is a function of f, the distance between the images ik and the distances between the image positions j and l. One example paper using this formulation is IsoMatch, creating informative grid layouts. Quadratic assignment is also one of the most obvious formulations for the shape matching problem. The following two papers are examples that use this quadratic assignment idea more explicitly than other papers. So I recommend these two papers as a starting point if someone's interested in quadratic assignment for shape matching. Joint segmentation is a nice example that is presented in this paper, and I like this example for the fact that it does some quadratic programming without being directly related to the quadratic assignment problem. So it's a nice example for another type of quadratic programming formulation. Fit and diverse sampling is the problem of selecting a subset of samples from a larger given set of samples, such that there are differences between the samples, so the samples are representative of the whole set, and each sample has a high quality measured by some function that tells you how desirable each sample is. This is an example of mixed integer quadratic programming for designing floor plans of buildings. An interesting aspect of this, in contrast to the other examples, is that here we really have integer variables and real variables that both contribute to the problem formulation. Also, we would like to briefly mention quadratically constrained quadratic programming. In quadratically constrained quadratic programming, we have now the objective function that is quadratic, same as before, but now the constraint functions can also be quadratic. We just have the general form for real variables here. Here we have the objective function, same as before, and here we have constraint functions. Now, before that we also used this matrix vector notation, but the matrix vector notation gave us a set of constraint functions. Note that here, even though we have vectors and matrices involved in the definition of the constraint functions, each of these only gives you one single constraint function. The constraint functions here have this quadratic term x transpose qix, where each constraint function has a different matrix qi involved in it, plus ci transpose x, so this is the linear term, and each constraint function has a separate vector ci involved in it. So x is the vector of variables, ci is one vector with known entries, and we have one ci per constraint function. So we have m constraint functions, and each constraint function has one vector ci that has n dimensions associated with it. The matrices qi are elements of Rn times n, so they are square symmetric matrices that have n square entries, where n is the number of variables. B in Rm is a vector, and each entry of bi is on the right-hand side of inequality I. So we have m components of the vector b, and each of the components is associated with the right-hand side of one equation, and we have m constraint equations. I didn't do too much checking of what papers use this, so I'll just briefly mention that when wanting to go from the real version of this to the mixed integer version, then one does the standard thing where some variables are restricted to be integers and others are free to remain real values. As a term, we have mixed integer quadratically constrained programming, or MIQCP for short. And this is also a level of difficulty that can still be handled by commercial solvers. Alright, we have now arrived pretty much at the end of this tutorial, that is a tutorial to integer programming. Some remarks to conclude. First, my experience with linear versions where the objective function and the constraint functions are linear has been pretty good. Even with many thousand variables, you often can get a good and reasonably fast solution. In many versions, you don't have to run the solver until it finds the global optimum. A solver can also give you an approximate solution, and often you can also get an idea of how close you are to the optimal solution. The quadratic formulations are quite tricky, and even though it's easy to write down a formulation, it's often not so easy to solve. So using standard technology for mixed integer programming, for example, it's not very easy to solve the quadratic assignment problem with more than, let's say, 10, 20 variables. It already becomes quite difficult. So my impression is that quadratic formulations are generally accompanied by heuristics on how to solve them. Also, my personal impression is that it's not wise to use anything else but Gurobi. So Gurobi seems to work significantly better than the other available solvers that I've tried. But these things are subject to change. So just my personal recommendation is, if someone's interested to start with this, is just to use Gurobi and try to experiment with a few problem formulations and see how well that works. All right, thank you for